nice weekend. I'm happy to be back after last week when you had the lecture with Robert Woodbury. I was in Taiwan in a whole-day workshop with the Swiss energy minister on the energy strategy of Switzerland and Taiwan. And it is very relevant for our topic today, and therefore you will hear about it a little bit. Just to position our place in the overall system where we are today, this is the overall course. In the first 3 lectures, you were dealt with the house, with the architecture, with the building as a system. Then last time you started with the system of the city and the urban sociology. You got examples. Today, we start with the big topic of stocks and flows. Stocks and flows, focusing on water and material. Who of you has heard or can imagine something with this word stocks and flows before? Or who of you has heard that in your previous architecture or urban planning lectures? No one? You just a little bit. Yes. Okay, I hope that by the end of the day you will see what kind of meaning it has for the city of the present and the city of the future, and obviously also for the city of the past. So this will be our point today. And in particular, we will have look first at the exercise 1. Thank you for sending it in. Many of you did, most of you did send it in. There were 3 parts. First was the reading of the documentation of the Minergie standard and also the LEED standard, which you did. Then the part 2, study this building where we are in and give a qualitative assessment on the sustainability of its design. And the third part was to explain why there is or could be a discrepancy between the standard that was anticipated, the amount of energy that was anticipated to be used, and which is actually used. The overall distribution of the exercise I quite liked. We have many that came in. Here's the whole list. And we have ordered them in a particular way. If it's okay with you, we would like to look at a few, very few, with you. And if the authors are here, I would like you to say a few words to that. It's okay with you? There were 2 identical documents from 2 students. I would like to talk to you about this after class. But if it's okay, is Stefan Breit here? Stefan Breit? Not here today? Okay. Then Philipp Grebac? Yeah. Yes? Okay. Would you like to say a few words to your exercise? We open it up. This is, no. It's the first one. Sorry, it's the first one. This one, yeah. It's in Italian, so maybe you can explain it a bit in English.
Oh yeah, it's just because I didn't find it.
You found the Italian one, but not the English one. Okay. Yeah. And but still, the explanation is pretty clear. I mean, this is taken straight from the documentation. And what was your major finding comparing the Minergie and the LEEDs? Yeah, take the microphone. Yeah.
Is in 2 words. It's the fact that Minergie label didn't take or take less in account the fact that the human being is actually using the house or the building, which has a lot of consequences on energy consumption, more than the terms of structure, heating, ventilation, and so on. And I think it's really an important thing to keep in mind. At the same time, there are a couple of critics or argumentation against the miniature, I think, at the moment, and the label, I would say, yeah.
Yeah, that's certainly a very important one. And this missing link between the human behavior, really, and the label is very, very difficult.
I have to say, I was pretty curious about these leads. How do it's called, like leads guidelines more than limits, because miniature is based on limits and definitions, and leads is more on guidelines where one will earn points, which is also a pretty interesting difference between the two labels. But it's, I don't know why, but I didn't find any leads guidelines or example, because most of the time it's you have to pay to get it, at least on the official site. I don't know. That was maybe a point.
So you didn't find a building that actually got these points, 50 or 60 or 70 or 80 points that you could.
I didn't get the leads guidelines, actually. I went to the site and it's you just have to pay them to get. I don't know if it's true or I just missed something.
I think you missed something, because the guidelines should be,
it's possible
should be available.
To get it.
Yeah.
Then I missed something.
Who did get the guidelines? Yeah, you did get them, huh? Yeah. So it is possible to get them.
Well, but it's only guidelines, but then it's not exactly written what you actually
right.
have to.
Exactly.
Right.
You don't have the process.
Right. That's right. Here, come to the front. You have the best view here, sir. And the system of the points, this is very good, but also it is before the building is actually built, and then what happens with it afterwards is not always clear. From what I gave you in the introduction to the exercise, the big range of actual energy performance is between a little lower than the normal building and up to 30 or 50% higher than a normal building. And that is, of course, again, the missing link between the human behavior and the guidelines.
Just also maybe link it to the function of buildings, because nowadays buildings can have very specific and different functions, from housing to offices to industrial buildings, and it's changed quite a lot on the different parameters.
Right.
That's maybe also an important point.
Okay. And finally, is this the last page, or is there one more? Here, this is a comparison of the actual building, typical building at ETH 6 years ago, the Minergy standard that it should reach, and what ETH hit. This building was calculated to be able to reach, and then you see those big differences at the bottom. These were the graphs and the numbers we gave you, and then you made your conclusion. Maybe you could summarize why you think the building is using more than anticipated.
I mean, yeah, I already told it, but as I said, the difference and the gap between the energy used in the other buildings of the ETH here in the Hengelberg campus, in terms of heating and ventilation, it's so huge. We have saw it on in the previous page.
Yes.
So we have to say, on one hand, it's very, very interesting, and in terms of materials and structure and how is it built.
And your assumption is the big ventilation loads are coming from. Can you go back to the last page? So these huge electricity loads here, they're coming from. Go back one page. And one back. Yeah, they're coming from this the server room in the basement here.
I can imagine, yeah.
Yes, and this is so. This is the right imagination, but we're still waiting for the exact numbers. but it must be, that must be the case, because otherwise there's no way you could actually waste so much energy in the rest of the building. And then, of course, you can go from there. If you start reflecting from this fact that this building is a Minergie building, but it uses much more, then if you go back, what is done with this energy that is spent on these servers? Is it only used for storage, or is it used for interactions? Do these interactions, these processes that you use in the basement, actually maybe save a lot of energy in other places? Are these processes that steer the behavior of other buildings? You don't know. It gets then really, really huge, the flow. But a fact is that a lot of the energy in the basement is used for storage, for running storage systems. And that brings us to the topic of today already a little bit, because storage, in our definition of stocks and flows, would be what, would you say? Is it a flow or is it a stock?
Stock.
What is it?
Stock.
It's a stock. It's mostly a stock because there's always some inflow and some outflow, but it's mostly a stock, or you could think of it as a stock. Stock and flows of information. So we have in this building the production of data, the production of knowledge, the production of information, and then we have a big stock of information stored in the basement where we don't exactly know what it is. But that also takes energy and contributes to the overall consumption. So thank you for your additional explanations. I quite like the exercises, as I said, that you did. The language is sometimes a bit difficult to read, but that comes from your different backgrounds, so that is not a problem. The main thing was for you to understand how the standards and the design and the finished building and the interaction with people work. And I think most of you did write that down.
Sorry, I had another
Yeah.
question on this point. Does it exist a label or something which has, I don't know, guidelines or whatever on what happens after the building is finished and it starts to be used?
When it starts to be used?
Yeah.
Yes, the so-called post-occupancy evaluation. That is an established process in the United States and many other places, in Canada as well. And there you can actually then compare. But to my knowledge, there is no formal, there is of course energy audits that test exactly how and if it performs to the calculations before. But in few cases, at least from the Minergie standard, you have to take actions afterwards. Yes, yeah.
I could just add to that. So, from what I've seen is the Minergie and the LEED standard. There is no necessary post-occupancy certification, but the 2000 watt Gesellschaft, they do look at the actual consumptions afterwards. And there's also another one which is here in Switzerland. It's this something, do you recall the name of it? It's the Society, no. There's another one. There's another one which does look at actual consumptions afterwards, but Minergie not.
You had another point?
I was just wondering, I was saying that...
Can you give him the microphone, please?
The cooling and energy that's needed for servers is something that's relatively easy to calculate, and it's sort of discrediting for the certification if they didn't calculate how much energy it takes to cool down a whole computer room. And out of all the things that we're trying to look for that are a reason, explanation for so much energy consumption or so much more than planned, a computer farm is something that you would have imagined we would have calculated from the beginning on.
Absolutely.
It's sort of weird that we
Yes.
forgot to calculate or...
They didn't forget, but as the standard was made originally only for residential buildings, nobody has a computer farm in its basement normally. That's why it was not accounted for. I mean, there's no way to put that into account in an energy building. You have to separate it somehow. But that building actually here was the starting point, one of the starting points to expand this standard to also commercial buildings to take account exactly of this fact. But still, when we look at how the electricity is measured, how the standard defines how much electricity you use for what process, this is still not measured in all of our buildings here. So you will never know, was that electricity really used for cooling or for pumping or for lighting? That is the problem.
Mm.
So between the building construction and the assumptions, there's still a discrepancy, even here. But the point is, in the end, what comes out of a building in terms of energy is heat. And if you add up all this heat over a city, then you come to the big numbers. And the big numbers, they have to be imported into the city first in terms of gas or oil or other things. And they are released as heat. And again, this is a very important stock and flow of energy. Energy flowing in, going out, being stored temporarily in the building or in the city, and then being released as heat and going back out to the atmosphere. That's another stock and flow we will study very carefully in the next weeks. Okay, so thanks again for the exercises. We just looked at one now, but the others are not similar. Of course, the exercise was similar. And again, the two students who did the same one, please talk to me afterwards. Okay, let's go back to the... yes, and the next one. There. So, you remember this picture? This is starting now the stocks and flow part. The stocks and flow here, it's the stocks and flow, what would you say? Is it, what is obvious that it flows and that is the stock of? Water, yeah, sure. And you can even see exactly where it's coming from. Obviously, it's coming from these mountains. It's going in this lake and this inlet lake, and it's staying there for a while, and then it's flowing out. And at the same time, these materials here, they also form a certain stock and flow. These are natural materials, so they grow. They're mostly bamboo. They grow as a grass within 5, 6, 7 years. You can see fantastic uses of this material right next door, where Dear Cable is working with the bamboo, as he told you in one of the lectures. And after a while, it starts to rot away. Also, the roof cover starts to rot away, and it turns into a flow again. Disappears. So it grows somewhere, it comes in as a flow, it's sitting there for a few years, and it flows away again. And so this was water mainly. And the other one is material. And material is, of course, you saw the bamboo before. I would say this is the next step of very, not rough material, but very simple material, very strong material. These are all bricks, air bricks that are used all over the world by now. And they are made in a process that takes a lot of energy, of course, to make these bricks. But then they are easily transportable, and you can build very quickly, rapidly, in addition one to the other, all these structures here from Rio. And also these bricks have a stock and flow. So they are made somewhere, they flow into the city, they're being put somewhere for a while, and then they are reused in another building, or they are demolished, and they become a flow again. This one is more complex stock and flow, but also of material. In principle, it's exactly like the one before, but the material has to be stronger. Here, you already have to use a lot of concrete. This is the example from Shenzhen, where you had the old plots that were sitting there, and then you just keep adding on the same plots more and more stories, And of course, you have to make this stronger. You cannot just do that with the normal brick. And if you do, which some people unfortunately do, then you have these collapses and many deaths. Connected to this picture is also another important stock and flow, and that is the one of density and space. That description you will find in no literature, because the stock and flow of density or space is very special to architecture, of course, and very special to urban planning. But density and space is also not a static entity. It's very dynamic. And in a city like this, in Shenzhen, density, which is expressed as, for example, people per square kilometer, is changing rapidly. In this case, it's just going up, 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 up. But in a city like Zurich, density after the 1960s was going down quite a bit. And now it's slowly going up again. So that is also, there is never really an eternal stock of density or space in a city. It's also moving. So there are the typical stocks and flows we consider in a city. The one of space that I described. Then energy, that you can go on forever. We had a little glimpse on it in the first exercise. Materials, we look deeper into today. People, the most important stock and flow. They come in, they go out, they stay for a while. Capital. This is a very abstract stock and flow, but still it can be treated as one. Water, the most important one, because there is no city without water, and no city can survive without water. And information can also be seen as a stock and flow. Like described in this building, in the basement, there will be stock and flow. We are now, as mentioned in the beginning, in the middle of the semester, so this is really dealing with the city as a system. You had the building as a system, now the city as a system, and in some cases, like water, we touch already the large scale, the territory as a system. You can also have different stocks and flows. You can do different things with water, of course. This is the one in Geneva. Water is not always used as purely a necessity or something which is very available everywhere, anytime, very cheaply. You can also use it as art, like here in Geneva. Or it has this incredible quality that it can also have in a frozen status, like you can see here in the mountains above Zurich. And you can then start to think how dynamic or how much flow you have in cities that are more in frozen areas rather than very liquid areas. Okay, before we come to the second exercise which deals with these stocks and flows, let's move to a more detailed description of the topic of stocks and flows. What is Is it one? Okay. So Rob, did you use that also last week? Not this one? This is using now a different technology, AirPlay directly projecting from here to there through the local network. But the air seems to be a bit thick here, so it's not so sharp. But actually, that's the resolution of this one is of course not equivalent to this huge screen. But I hope you can read it in the back. Now I lost my. So this is what we want to discuss today: stocks and flows. This is my favorite, one of my favorite images, because here you can see all those stocks and flows together. This is another example from a country far away from here, from Myanmar. Who is living closest to Myanmar?
Singapore.
Singapore, yeah, that's pretty close. Just an hour's flight. Anyone in the north? China, India, Bangladesh? Cambodia? No? So Myanmar is north of Singapore at the west coast of this huge subcontinent. And it is very beautiful country, very original. It has a huge river coming from north to south, the so-called Irrawaddy River. And this river is totally untamed. It causes huge floods, lots of damage if people are living where the flood is coming. And on the other side, it also brings a lot of benefit. It's a very good example for these stocks and flows that we are discussing. Here's the river, and here's all the stuff it brought in the last years, decades, centuries, I don't know. And on the top, you have another stock and flow. So the river comes down when the ice is melting in the mountains. It floods huge areas, thousands of square kilometers. And it deposits all kinds of very fertile mud, if you want, which it brings from the mountains. And then it recedes and just keeps flowing through the summer. The mud stays there, and immediately it starts to grow. And people come and they resettle this flooded area every year. And they bring, of course, seeds with them. And they put the seeds there. As you see, it grows immediately. It's wonderful. And they can harvest, sometimes even twice, during the dry, so-called dry period. Not only do they have a stock and flow of water, of material, but also of their food. So it goes from seed to food. Then it is exported. Even the buildings, the temporary buildings that are there, they're also a stock and flow. They come in as simple beams that you bring here and some temporary material. They make these temporary buildings very quickly, bring in the animals. The animals with their manure, they also put some fertilizer on the whole place, and it goes away when the next flood is coming. So it's a typical stock and flow operation, if you want. The concept originated in the 1960s, as I said before, and best known, it's for finances. Stocks, these are quantities that do not move, and flows are quantities that do move. The flows are measured quantities per time. The differentiation between statics and dynamics makes the principle applicable to architecture, which we normally or quite often see as a static art or product, but it is in fact very dynamic. And a city is even more dynamic. And in our opinion, it is not possible to understand a city, how it works, and how to design it for the future or to improve it, if we do not understand these stocks and flows of a city that we listed before. The stocks and flow of material, of water, of people, of finances, of information, and so on. The stocks and flows, you find definition of that in the book. So you can read the position. There are some very good examples related to finances. Here this one says, for example, the US nominal gross domestic product refers to a total number of dollars spent over a time period, such as a year. Therefore, it is a flow variable and has units of dollars per year. In contrast, the US nominal capital stock is the total value in dollars of equipment, buildings, inventories, and other real assets of the US economy. So buildings are seen as real assets, so they become like a stock. There are also some quite good websites where you can see the explanation, the interaction. I'm not sure if it works. I tested it on another machine, but maybe not here. Anyway, when you open this website on the internet, then you will see how the stocks and flows have made nice animations, how the flow of money goes up and down over the year, and the stock of money is reacting accordingly. The most important one is water, as I said. There's also stock and flow of energy, which I do not want to go into now. But the stocks and flow of material is a very important one. And I want to bring you one example, which is the material of concrete and the city of Zurich. Do you think it is possible to detect the change of a city, the lifestyle of a city, from looking at the material flow of concrete in and out of a city? Do you think that's possible, or? No idea, huh? I didn't believe that, but when I saw these numbers, it was very clear to me. Anyway, the stock and flow of concrete in Zurich looks like this. Somebody here at ETH in 2009, 2010 made a very interesting paper. It's called Entwicklung einer Ressourcenstrategie für mineralische Baustoffe für die Stadt Zürich. And it's online, you can find it. But it has literally this idea of stocks and flows built into this illustration. On the left side, from the left side, we have the flow of concrete. And when concrete is fresh, it is actually a flow. It comes in as a fluid. And then it goes into these different parts of the building, of a city buildings. And here you have the flow of concrete into infrastructure. Infrastructure would be everything underground, the streets, viaducts, train, bridges, and so on. And the stocks and flows of buildings. So this is going into the buildings. And you can see already quite a difference. You have 624,000 tons going into buildings as a flow of concrete, only 52,000 tons into infrastructure. And then you can, in buildings, you can see even more differentiation. EFH means Einfamilienhäuser, single-family homes, multi-family homes, and offices. And you can see already the big change between single-family homes, not many in Zurich. Not much was done in this year in terms of flow going into single-family homes. Multi-family homes, that means apartment blocks and so on, 277, and even more, 329,000 tons into office buildings. And so you can see this is quite interesting. This is going in. And then out, what goes out here? From single-family homes, only 4,000 tons were taken out and not thrown away, but mostly recycled. And then from multifamily homes, only 39,000 tons were taken out and recycled. And offices, 160. So there was a lot of remodeling probably in the offices. And then the same for the infrastructure in the streets and other infrastructure, are more modest. It was only 1/3 of the total coming out. But you can see from this difference already how the city has changed. It has gone from taking out industrial parts, old industrial parts, and replacing them mainly with new office buildings and mainly new multifamily homes. Then you see, so this is the actual construction process. It becomes a stock, and out of the stock, also the old stock is extracted. This is then the collection of the old stock, 276,000 tons going out from buildings, 103,000 from infrastructure. Then much of this is recycled. Actually, 319,000 of this is recycled, and only 60,000 is thrown away on the so-called deponie. And then of this recycled one, you make new building materials, and you can see much of this is going back into the city. So it's like almost a cycle. Only relatively little gets lost. There's 60 here, 60,000 of the overall 670,000. If you had a city like Singapore, it would be even more radical. What do you think? In Singapore, you would have more recycling or less recycling than in Zurich?
Almost all of the concrete is recycled.
Exactly.
Because there's no space to throw it.
Exactly. And that is amazing. First of all, you don't understand why, but you understand it very quickly if you look at the stocks and flow of finances and the stocks and flow of available materials. Because we know that in Singapore there's a great shortage of sand and other building materials, so you almost have to recycle every bit of concrete in order to use it, whereas here you have more than you need in terms of material. If you come to a city like Shenzhen, what do you think is the recycling of the stock and flow of material? It's almost non-existent because the flow is just going into the city. There's nothing out because the city is growing so fast. There's almost nothing going out. Everything is staying there, and it's just a huge flow of material into it. Anyway, I think this is all in German, but here's a quick English description. And this is this stock and flow of a city material. The first step is to define the system boundary, which you always have to do. And here we just took the system boundary of the city of Zurich. And then in a particular year in 2005, they saw that 670,000 tons concrete gravel flowed into the city and 379 material left the city boundaries. And half of the inflow, 329 tons, went into new office buildings, which at the same time produced with 160,000 tons also the highest outflow. The present increase of population of Zurich is reflected in the 270,000 tons of concrete flowing into the city apartment buildings and only 39,000 tons from demolished apartment buildings leaving the city. So I just want you to get the view for this. If you take a city like, let's say, Detroit, where you have a different materialization of the buildings, the stocks and flow would be completely different. If you examine Singapore, we heard has a much higher, even higher stock and flow of material and recycling. And if you take something like the very first one that I showed, where you have the lake in Myanmar, you have an almost complete cycle. It comes in, it stays for a while, it goes out. So this cyclic building life cycle is almost perfect in the first example, and it is unbalanced in all the other examples. But if you know that, you can start to understand a city better, and you can start to plan a city better. Because with these stocks and flows, of course, it is a huge strain on energy. So if you look at the stocks and flows of energy, this one being Switzerland, we can see the whole energy which is used for the production of buildings is not shown here. This is just the maintenance of buildings and the keeping them warm in the winter. And the production of buildings is somewhere here in the factories and some of it in the small commercial places. but the majority of the material is produced probably somewhere outside of the country. So this would be the system boundaries of this one would be the state of Switzerland. But in the state of Switzerland, you can see a lot of different flows of energy from the energy supply here in terms of crude oil, of normal petroleum, of natural gas, of nuclear power, of water power, which is all being transformed then into the end use here on the right side in residential buildings, in factories, in commercial buildings, and in transportation. So there you have also example for stock and flow, interacting with the other stocks and flows of a city. And finally, the stocks and flows of water. Very obvious, again, the example of Singapore. The interaction between the city and the water is very, very obvious. As a matter of fact, the water was the reason why people were coming to Singapore in the first place as a trading place. And you know the oldest building in that image, of course. It's now a hotel, but what was it before? It was the post office. So this was the biggest building of Singapore for a long time. It was the British Post Office, and it was also at the deepest part of the port. In the meantime, it's dwarfed by these gigantic buildings here. And these gigantic buildings here, for example, all of those on this side, you know them very well. These are the new finance center, which regulates the stocks and flows of finances into the city and with the city. So this part, finances, this part, some living, some also finances, and the old part is almost not visible anymore. And everything has been done with landfill because we're looking from a place that didn't exist before onto the old city. So that's an example from Singapore, or this is an example from Hamburg, which is also very dependent on the stock and flow of water coming in and out of the city, because all the material goods come on the water into the city and leave it to a degree with the city again. And here the other fantastic stock and flow, or the quality of water that it can freeze, so that you can have a huge stock of water which is actually turning into an ice block in the winter, and then you really have a stock. So these are some examples. There are other stocks and flows that we look at in more depth next time. Of course, wood is one of them, stocks and flows of wood. We have stocks and flows of food, very important for the energy, the stock and flow of capital, and the stocks and flow of land. I want to show you this because this is seen from the other side. The picture of Singapore taken before was taken from down here looking this side, and now we're looking from this tall building down. And the significant part of this is that all of this land that you see has not been there before. So they have turned the land into a flow of land into the sea, made artificial land, becoming a stock, and now being used as a stock until, who knows, it's been taken away again in the future. So how can we calculate all these different stocks and flows? Because we need to make some quantitative relations between them. They all interact in various ways. And if you want to represent a city as a system, then we have to define these interactions, at least to a degree. This will be your second exercise. Don't worry, you don't have to write the world formula for the interacting stocks and flows of a city, but you should select and define the city that you find most attractive from your point of view, and you should consider as much as possible the stocks and flows in that city. Let's go back to the original presentation. No, advance. Advance. From this slide to the next. Okay, so here is the second exercise. These are the factors of livability. And livability is one of the most decisive features of a city. As a city is not livable, it's not attractive, the tax base is going down, so you have very high demand to make the city more livable. So it's one of the most important competitive advantages of a city, if you make it more livable. The city that you are in right now, Zurich, according to different measures, is always number 1 or number 2 on the livability index of the world. So it's a very livable city. And so the exercise is simple. It's not as work intensive as the first one, because you don't have to do lots of studying. You have to do thinking and deciding out of your emotions or feeling, if you want. So the first thing is to list the most livable cities that you know, building on your own experience and judgment with the most livable city at the top of the list. It doesn't matter where the city is, what it is. Just list the one that you feel is the most livable for you. Second part, describe in your own words 5 characteristics defining the livability of a city, and order them with the most important at the top of the list. That could be, I don't know, because it's nice weather, or lots of money, or nice people, whatever. Typically, you will end up with one or more of these stocks and flows that we discussed. And then part 3, for each one of the city, you select, if city data are not available, the Gini coefficient. You know what that is? You'll find out. Gini coefficient is very important. That is an expression for the equality or inequality of the population of the city. The GDP, the form of government, governance of the city, and the surrounding country, the latitude and the mean annual temperature. So these are just facts that you have to give. First, you decide which is the city I like most. Then you analyze why is that. You give those numbers, and this is the whole exercise. To help you a little bit, there are many, many rankings. You know, the Global Livability Cities Index, the EIU, nurses, monocles, major cities, all of this is existing on the internet. Your colleagues from last year, actually, they made a very good interface. Can you go to the next one? Yeah, can you, no, to the website. So they actually made a website where they have listed already the existing rankings, so the most livable cities in the world. For example, go for the Mercer, the first one, yes, and click, and then you get displayed in the whole world where the most livable cities are. And then, more important, if you click to one of them, for example, Zurich or Frankfurt, doesn't matter, yes, then you already get quite a number, a set of numbers. They put that together already for you and for the other students. But if you check those numbers and compare it then to the livability of the city or how it's ranked, you see some very interesting relations. For example, they list the CO2 emissions per person, the energy consumption per person, the energy consumption of residential buildings, the length of public transportation network, the annual water consumption per person, the waste per person, the share of waste recycled per person, the average daily nitrogen dioxide emissions, the environmental governance, how this is done, and where it is situated on the Green Cities Index overall. So you can see a few quantitative things that relate to stocks and flows, but that doesn't tell you the whole story. But it gives you the opportunity to link it to the actual performance of a city. Okay, so this is background material that you can use, but you should make your own decision and write your own criteria why you think this city is the best in your opinion, from the standpoint of livability. Think of yourself and think of your own future. Okay? So, thank you very much, and have a very good week.